Hello everyone, this is Dr. E, and for today we're going to be proving the Pythagorean Theorem. Proving is one of probably the most challenging skill that we need to learn in geometry. For today we're going to be using our skill in proving to see if the Pythagorean theorem would work to any right triangles, no matter how big or small our right triangle is. So to do that, we know that the Pythagorean theorem is the formula that we use to find the missing side of a right triangle. So let's say I have a right triangle right here, and we need to find the missing side of our right triangle, which is the hypotenuse. The famous formula to use to find the missing side of this geometric figure would be the hypotenuse squared is equal to the square of the leg plus the square of the other leg. And since we are looking for the hypotenuse, we're going to use the given information that we have for this right triangle, which is one of the legs is equal to 3 and the other leg is equal to 4. And by using the formula, we'll be able to find the hypotenuse squared, which is equal to 9 plus 16. And 9 plus 16 is equal to 25. And to be able to get rid of the square to our hypotenuse, we'll take the square root of both sides. So we have hypotenuse is equal to 5. So now that we're able to find the missing side using the Pythagorean theorem, we know that this formula or the Pythagorean theorem is what we needed to be able to figure out the missing side of this right triangle. And another way to write the Pythagorean theorem is with c squared is equal to a squared plus b squared. And this is what we're going to be proving today on how we're able to come up with the formula that we are using to aid in helping us to solve a geometry problem similar to this one. So let's start with the right triangle, which is what we need to use or what we are using to establish or to show how the Pythagorean theorem works. So we are not sure yet if this is indeed a right triangle without its marking. So let's put the right angle right here to show that we are using a right triangle. And let's call the shorter leg as A and the longer leg as B. And of course, the hypotenuse as our C. So this is now our sides of our right triangle. And the two corners that we are seeing here, let's name it as angle A and angle B, or angle alpha and angle beta. And from here, angle beta is opposite side B and angle alpha is opposite side A. And of course, the right angle is opposite the hypotenuse or side C. Let's duplicate this right triangle. So we'll be able to construct another geometric figure that is a square. And to be able to do that, we're going to be using our existing formula that we use in geometry. And we'll start with this side right here and the triangle. Now, focus your attention on the yellow right triangle that we have. So we know that these four duplicates are all congruent and they're all right triangle. And angle alpha and angle beta will be able to figure out a way on how to measure the sum of those two angles by using the theorem for the sum of the interior of a triangle, which is equal or always equal to 180. And with that in mind, we know that the sum of angle beta and angle alpha should equal to 90 degrees because 90 plus 90 is equal to 180 degrees, and the sum of the interior angles of any triangle is equal to 180 degrees. And another way of showing it is seeing that the straight line is right here is equal to 180 degrees. And if we put angle B and angle A or angle beta and angle alpha right next to each other, we'll be able to come up with a 180-degree angle by establishing the right angle that is missing on this little piece right here, which is an important fact or important markings that we are establishing in our proof, because now we know that we are seeing a right angle in between or right next to angle beta and angle alpha. So if we construct a square out of the four right triangles that we have, we can be sure that we are seeing a square, which is what you are seeing right now with the pink right triangles, and another square inside the bigger square. And these are the shapes that we're going to be using with our proof. But first, let's focus our attention on our bigger square. So let's try to figure out a way on how to find the area of that bigger square. So we know that the area of a square is equal to side squared, and to be able to establish the measurement of the side of our square, we are seeing that the base or the legs of our right triangle can be our side, or the sum of them will be the measurement of one of the sides of our square. And since it's a square, we know that this side is congruent to this side. So if this is a plus b, the other side of our square is also a plus b. And now that we know the sides of our squares from our right triangle, let's find the area of that square using the formula of a square, which is equal to side squared. Side being a plus b, and by squaring it using our special product, a plus b times a plus b is equal to a squared plus 2ab plus b squared. And now we're finished with our first part of our proof, which is finding the area of that big square that we're able to form using the four right triangles. And what we're going to do next is to look at our figure on a different perspective. Now we are seeing that we have four right triangles, and we also have a big square inside our pink square. So now we are seeing a total of 5 shapes in our figure. And it's 5 shapes because of the 4 right triangles and the square inside it. And if we dissect our figure, we are seeing the 5 figures that we can calculate using the existing formula of the four or the 2 basic figures that we are seeing, and that is the square and a triangle. So the formula for the triangles, let's see how many triangles can we use for this formula. We are seeing 4 triangles, so all we need to do is to add them up, and to add up the blue square that we have from the piece of this figure that we're able to form using the 4 duplicates of our right triangle, and we're going to do that using geometry. So our square is basically formed by the measurement of the hypotenuse of our 4 right triangles. And if we're going to add them all up, we'll be able to find the area of this square on this perspective. So we'll add the 4 right triangles and the square right here, and let's see if the sum of these shapes will equal to this formula that we are using in our first shape that we established a little while ago. So let's start working on finding the areas of those little triangles, which is half of a times b, and the square, which is sides square. So since the measurement of our base is a and the measurement of our height is b, using algebra, we know that the 4 triangles is going to equal to half AB plus half AB plus half AB plus half AB plus the area of a square, which is c to the power of 2. So now that we have our equation, all we need to do is to use our algebra skill to simplify our equation. And we are seeing half of AB plus half of AB, which is equal to 1AB, half plus half is one whole, half plus half is one whole. So now we're seeing two wholes of AB, so we have 2AB plus C squared. And now that we're able to simplify the formula of the area of this figure, we know that this shape is similar or equal to the formula that we are able to calculate a little while ago, which is a squared plus 2ab plus b squared. And by equating it to each other, we are seeing that we can cancel out 2ab and 2ab, and by simplifying our formula, now we are seeing a new equation that is quite familiar to all of us, which is equal to a squared plus b squared equals c squared, and we know that this is the Pythagorean theorem. So this is how we can prove our Pythagorean theorem using the facts that we know in geometry, and now we're able to establish that the Pythagorean theorem would work to any right triangle, no matter how big or small it is. So as a recap, this is the first problem that we calculated using the Pythagorean theorem, and we're able to prove the Pythagorean theorem using our right triangle, and we duplicate this right triangle into 4 right triangle so that we'll be able to form a square. So by duplicating it, we have one triangle, we have the second triangle, and we're just going to put alpha and beta right next to each other. Alpha and beta right next to each other. And by doing so, we're able to create our square. And from this square, we're able to find the area of the outer square and the area of the sum of 1, 2, 3, 4, 5 geometric figures. That's why we're able to come up with c squared is equal to a squared plus b squared, which is the Pythagorean theorem, which is what you are seeing in our screen right now. So this is how we are able to prove the Pythagorean theorem. So your number bender challenge of the day is, let's see if you can think of another way on how you can prove the Pythagorean theorem using your method. And that is our lesson for today in geometry. So proving may be a little challenging, but this will help us in gaining our confidence in answering math problems and also training our brain to think analytically, and that is basically what we did in our lesson for today. This is Dr. E, and see you again next time.